Good morning. In the last two sessions, we had some basic idea about the bar magnet. We studied about what's a bar magnet and what is magnetic length, magnetic dipole moment, and what happens if a bar magnet is cut into two equal parts. Now today we'll see what happens if a bar magnet is placed in a uniform magnetic field. Now when a bar magnet is placed in a uniform magnetic field, it experiences a torque. Placed in a uniform magnetic field, it experiences a torque. I will write as shown in the figure. That means the bar magnet is placed in such a way that its magnetic dipole moment makes an angle theta with the direction of the magnetic field. I'll show you the figure. So when a bar magnet is placed in uniform magnetic field as shown in the figure, it experiences a torque. Now first we'll write the figure. This, let us say this is the direction of the magnetic field B. Now bar magnet is placed in such a way that its dipole moment makes some angle theta with the direction of the magnetic field. Now this is our magnet. I'll say this is the north side. The magnetic moment is in this direction. So the magnetic moment makes some angle theta with the direction of the magnetic field, external magnetic field, that is B. Now if you take this angle is theta, this is the external magnetic field B. Now the force experienced at this as MB, and at this side is it is minus MB. Now the torque is, so these two forces form a couple. The torque is force into perpendicular distance. Now if this is theta, and we know we take this total length as 2L, so this length will be 2L sin theta, because theta is this, so this is the opposite side. That is the perpendicular distance between the force. One force here, another one here, so the perpendicular distance between the force is 2L sin theta. Now the torque experienced is given by torque tau. We always know torque as force multiplied by perpendicular distance, that is 2L sin theta here. So this is actually here I will write this as this is M. I'll take M as the pole strength, so M into B, the pole strength. The force is M into B, because capital M, if I take capital M is the magnetic moment I am taking, so small m will be the dipole moment is capital M, M will be the pole strength. Force into perpendicular distance, force into distance, perpendicular distance between the force, so that is M into B into 2L sin theta, or this can be written as torque is, we know what is capital M. The magnetic moment, the magnetic dipole moment is given by M into 2L. So this can be written as 2L into M can be retaken as M. So this is MB sin theta. The torque experienced is given by MB sin theta, or you can write torque in a vector form as M cross B. In vector form, torque as M cross B. Because it is MB sin theta, M cross B will be the vector form. Now because torque is MB sin theta, we can calculate when is the torque maximum and when is the torque minimum. Now the torque experienced is given by MB sin theta. Now say case 1, if theta equal to 0 or 180 degree, then torque is 0, that is minimum torque equal to 0. That is, when the magnetic dipole moment is parallel or antiparallel to the direction of the magnetic field, then it does not experience any torque. Theta is 0, what exactly it means? If B is in this direction, M will be in the same direction. The magnetic moment and B are parallel to each other. Or in another case, 180 means if B is in this direction, M will be anti-parallel to it. If N and B are anti-parallel to it, then also torque is minimum. Theta is 0 means that when the magnetic dipole moment is parallel or anti-parallel to the direction of the magnetic field B, then it does not experience any torque. We can write that sentence: when magnetic dipole moment M is parallel or anti-parallel, parallel or anti-parallel to the direction of magnetic field B, then it does not experience any torque. When magnetic dipole moment M is parallel or anti-parallel to the direction of magnetic field B, then bar magnet does not experience any torque. Now we'll take another case when theta is 90 degree. When theta is 90 degree, what about torque? Torque is maximum because sin 90 is 1. Torque maximum will be equal to MB. Now this is the case when the magnetic dipole moment is perpendicular to the direction of magnetic field, then it experiences maximum torque. When magnetic dipole moment M is perpendicular to the direction of magnetic field B, then the bar magnet experiences maximum torque. it experiences maximum torque. Okay, so now we know when the torque is maximum and when the torque is minimum. So this is a particular case where if B is in this direction, then your magnetic moment is in this direction, so 90 degree. Theta is 90 degree, the torque is maximum. So the torque always tries to align the bar magnet in the direction of the magnetic field. Now next we'll say what is the work done in rotating the bar magnet in the uniform magnetic field. I'll give you the equation. Work done in rotating a bar magnet, work done in rotating a bar magnet work done in rotating the bar magnet work done in rotating the bar magnet through an angle theta in uniform magnetic field is given by cos theta minus mb cos theta. This is the work done in a uniform magnetic field. Or the potential energy stored in bar magnet making an angle theta with the direction of the magnetic field is minus mb cos theta. In another way, potential energy stored in a bar magnet making an angle theta with the direction of magnetic field is with the direction of magnetic field. Generally potential energy is represented by U. U is equal to minus mb cos theta, or actually it is the dot product. Okay, so the potential energy is minus mb cos theta. Torque is given by mb sin theta. Potential energy is minus mb cos theta.